Good morning, good afternoon, good evening, whenever and wherever you are. My name is Anna Rochelle, and today we're going to talk about transformations of graphs. And one thing that I want to make sure that you know is if you're an earlier Algebra 1 student versus a seasoned Algebra 2 student, you'll know some of the functions a little bit better in the way that they look as their original functions versus, you may not know all of the functions that we have, right? So I'm going to share with you transformations of graphs in their individual form. You can absolutely multiply, use multiple of these transformations in one function. So meaning you can have a vertical translation up with a reflection over the x-axis and a horizontal stretch. And all within one function, that's totally fine. It's just a matter of being able to put them together. But before you're able to put anything together, you absolutely need to understand what they are individually and how they look individually. Okay, so before we get started, one of the things that I want to make sure we know is what some of these functions look like. So one thing that I want to make sure we also know is that whenever I see f of x, I can always replace it with the letter y and vice versa. They are interchangeable. They're the same exact thing. So I could actually have this as the function of x, right? The function of x every single time. And it won't be any different. Now I know as middle schoolers, you learned about y equals all of these things. And later on in middle school, you tended to learn about the function and function notation. But I want to make sure that that's very clear. They are the same exact thing and they are fully interchangeable. Okay, so this function we know is the regular x function where every value of x equals every value of y. So you have multiple points that are the same number, right? 0, 0, 1, 1, 2, 2, 10, 10, negative 100, negative 100. Those are all the same, right? This is called my absolute value function. So my absolute value function, it makes sure that we know that every value in my absolute value function, every y value has to be positive in the original function because absolute value is actually just the distance from 0. And that's always going to be positive, right? This is called an exponential function, where it starts off super low, almost touching the x-axis, but not quite. Again, if you're a seasoned Algebra 2 student, you know that it's more of a asymptote. The x-axis is an asymptote. So again, if you're an unseasoned Algebra 1 student, you'll learn that later on in your course. So it starts off super low and then it goes really high, like exponentially high. I feel like gas prices are usually exponentially increasing because they just go up, 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 right? And this graph is called a quadratic graph. Quadratic, not quadrat. What the heck was that even? Quadratic. Okay, a quadratic graph, and that just kind of looks like a U shape. Now I'm going to use different graphs during the course of the video to explain different types of transformations. So the very first thing that I want to mention is all of my vertical translations and transformations are going to be in blue and all of my horizontal ones are going to be in green. And one of the things here that I also want to mention is every time we see a vertical translation, what's going to happen is I'm going to actually kind of have the translations make sense, right? If I'm moving something up, I'm obviously going to add, right? If I'm moving something down, I'm obviously going to subtract. That's kind of like just general knowledge of a number line, right? Whoops, where is my, okay, here we go. So what this graph does is it actually looks like this. My original graph starts off with x squared. And then as I move up, that's going to be my same exact graph. I know they don't look quite exactly the same, but my same exact graph should go up. And every single point along my U shape is just going to literally go up. And that's it. Again, the same thing is going to happen to my graph moving down. It's going to just scroll down a little bit and then it'll be the same exact shape, right? So when we have a left and a right translation, again, if you are seasoned Algebra 2 students, you understand why x plus 5 is moving to the left instead of the right, because generally speaking, when we add, we're thinking of moving on the right-hand side of the number line. However, later on in an Algebra 2 class, if you haven't yet covered it, you'll understand why. I don't want to get into this now because it's an entirely different lesson. So just for now, trust that that's the case. And so with horizontal translations, you're kind of like flipping your logic, right? So what that's going to look like is we're going to have, again, my original x squared graph. Anytime we move to the left, we're going to add 5, but we're going to add 5 within the parentheses, within the brackets, within the absolute value sign, within the whatever form of grouping we need. And again, that's because it's all going to be horizontal. Horizontal things move along the x-axis, and because they move along the x-axis, we have to attach our number to the x, whereas vertical translations do not move along the x-axis, they move along the y-axis. We can just have them kind of like join us for the ride. Okay, so again, you can move like this green one, you can move it to the left and then you can move it down, or to the left and move it up. And then you would have like an x plus 5 inside the parentheses and then plus 2 outside of the parentheses. So now let's talk about vertical stretch and shrink. And this is something that most students really start to like freak out about because, oh my goodness, what's happening? But I for sure believe that you can do this. So take a look at this. When I'm stretching something, imagine I'm stretching you by height, right? Like imagine I'm taking the top of your head and the bottom of your toes and just pulling them apart. That's a vertical stretch. I'm increasing your height, right? When I'm shrinking you, I'm again going to take you from the top of your head and the bottom of your toes, and I'm going to smush you together. I'm taking care of your height. So vertically, this is a height difference, okay? Versus horizontally, imagine I'm pulling you apart horizontally, you're getting wider instead of taller, right? So we're going to talk about that in a second, but I do want to go ahead and take a look at this. So I use the regular x function, the linear function, in order to show this. So I have an x function, which kind of looks like a linear function, which it is. And when we have 10x, I know that we go up 10 and over 1 in order to show that linear function. So I'm going to be in a tall linear piece, right? It's going to look like it's stretched up down. Versus this 1/10, it's kind of like laying more flat. Now, this is the difference between a vertical stretch and shrink. We're moving up, down, again, along the y-axis, okay? Now, the other piece is, see how there's no parentheses, right? And because there's no parentheses, what's going to happen is we're just going to leave it as is. So now when we take a look at horizontal, again, we're going to flip that logic. We're going to flip that piece of information. So a stretch, instead of being multiplied by 10, we're actually doing 1/10. And a shrink, instead of multiplying by 1/10, we're going to multiply by 10. But again, it's going to be within whatever absolute value, brackets, parentheses, whatever symbols, whatever groupings we have, because it's horizontal and it needs to be attached to the x-axis. So let's take a look at what those guys look like. So my absolute value of x looks like a v function. When I'm shrinking this, I'm shrinking it horizontally. So I'm shrinking it from like your shoulders. I'm like pushing you in. And when I'm pushing you in, I'm kind of like stretching you up, right? Which means when I stretch you vertically like this, that's why these guys look the same. And that's why these other guys look the same as well, right? When I'm stretching you and I'm pulling you apart at your shoulders, I'm making you wider. That's why this graph right here, this lime green graph right here, looks the way that it does. Okay, let's talk about vertical and horizontal graphs. Now, the reason why I chose this exponential function here is because it just looks so much better and so much easier to explain. So again, if you're a seasoned Algebra 2 student, you know exactly what an exponential function looks like, but if you're not, you will eventually learn about what they look like, how to graph them, and all that jazz. So vertical reflections would reflect along the y-axis, right? Because everything that's vertical has been going along the y-axis. So it's going to go from the top of the x-axis onto the bottom, right? It's going to reflect along the y-axis. And so if we take a look, this is going to be my reflection, where I'm reflecting across, right? I'm reflecting the long way. My horizontal reflection is going to reflect along the y-axis, and it's going to reflect left to right. Yeah. So with that in mind, the reason why here my function, my entire function is negative is because I need it to be a vertical reflection. My negative will not be on my x. However, horizontally, when I translate, when I reflect, when I do anything along my x-axis, here my x becomes negative. And that's the main piece that I want you to remember. Anytime there's something horizontal, we're doing some sort of change to the x-axis. Anytime there's a vertical transformation, we're doing something to the entire function. So that's the biggest change. And then you can always match them up and do two things in one function or more. You could have a reflection, rotation, whatever, in all of the other functions. I hope that this was helpful. I will see you in another video. Bye.